Yeah, thanks for the intro, Kimberly. Again, my name is Gingeleski. This talk will be how to thwart malicious automation and kick bot butt for $0. Together, we're going to discuss anti-bot security and countering abusive scripts that target our web apps. We'll go over where architecturally you might detect and react to such activity. And if you're missing any of those components now, the good news is we'll talk about a lot of open source software and vendor agnostic tactics. We'll cover 3 or more, well, more or less distinct ways to detect bots. We'll do a brief threat profile to understand who we're engaging with. There'll be plenty of practical maneuvers and strategies to utilize versus threat actors. I'll also overview how you might mature an overall environment and where you might place your protections and other security appliances to more effectively counter bots, doing less manual work and trying to achieve a more hardened attack surface. There'll be a demo walkthrough of pure open source, trying to highlight the different components of an anti-bot program on a Vagrant box that you can grab yourself if you'd like. That just shows, I guess, everything to working together in the talk, open and effective. And we'll also end on a realistic note and try not to break any hearts. Briefly, who am I and what do I know about this stuff? I'm doing security engineering right now for a cryptocurrency exchange called Bullish. It's bullish.com. Arguably, dealing in digital cash can make you a popular attack target. So we've given a lot of thought to anti-bot. And before this, I did pretty much the same while maturing the product security program for HBO Max, the now infamous streaming service. I joined there in 2020 before its public launch, sort of laid the groundwork, what's projected to be 70 million plus subscribers by the end of this year. Then earlier than that, I've been a traveling hacker pen test consultant person, including with AppSec security, a fallen entity, strong OWASP ties. Before that, developer. So overall, it was a lot of exposure to the internet and spending a lot of time on the internet. Away from the computer, I'm a student pilot, flying planes around. Also enjoy shooting sports. Currently live in South Florida, but spend a lot of time in New York City as well. So feel free to reach out to my OWASP email, which is later in the deck, about anything or meeting up. Happy to chat. A quick couple of disclaimers. The newer original part of our discussion is really how to set up and operationalize an anti-bot program. For example, if you're in a pinch without any protective measures already in place, like age CAPTCHA, you might fingerprint your attackers, the order of their incoming request headers, and then block that using mod security, and then have varnish in front of that, making mod security's blocked responses look like normal negative responses from your service. Pretty decent at just stringing things together and doing that. But the actual bot detection methodology and fingerprinting techniques, the science behind much of this, I have to give credit elsewhere. There are a lot of open source authors that have just very generously published works, and I've linked a lot of them in this deck. They move the state of this field forward a lot more than I do. And then also, this content doesn't necessarily represent the user programs of my clients, employers, past or present, any of that. So the bots were coming. If you put any new web app on the public internet and it has what even looks like a login page, it's not really a question of if bots will show up, but more of when. You can test this pretty easily yourself, and I've linked an open source project I like called Hellpot, which its author describes as a portal to endless suffering meant to punish unruly HTTP bots. You can stand that up on a tiny VPS, like pick your favorite cloud provider, and without even configuring DNS around it, you'll start seeing probes in, I'd say, under a couple hours. So of course, bigger, more publicized apps with bigger user bases will draw more fire, but the point remains that on today's internet, basic bot defense skills are for every web defender. we'll contextualize where and how we're going to protect ourselves by just considering how contemporary web apps are laid out. This very simple way of standing up a web app is still totally valid, just a single box or VPS. These internal components I'll better define on the next slide, which is going to represent a fancy application worth maybe 6 to 10 figures in fiat currency that would look like this. Just a good deal more complicated and spread out. An HTTP request that's coming in might travel through initially a CDN edge, there's possibly computing right there, then hit an API gateway, web application firewall, and I've seen setups too. And then eventually you'll get to logic that might fire for in-client fingerprinting or in-client bot detection, and then finally hit origin. So there's a lot of bouncing around of where this request is going before it actually gets to your service-based logic. My presumption being it's something you've developed in-house or at least pretty customizable. Hopefully, as traffic is flowing through all these pieces too, there are logs that are being written out because logging is huge and I think underappreciated and just very important to understand what's going on within your own application. It's ideal also for you to be piping all the log data into a log aggregator, by which I just mean something like Splunk indexed data or ElkStack to be open source, Elasticsearch, Logstash, and Kibana. Because if you have a ton of logs, but you can't analyze them and glean actionable insights, then that's not really worthwhile either. If we work backwards on these components from origin and elaborating a bit more on what each can do, origin allows you the opportunity to do, I guess, any of the security stuff you could do earlier in this stack, since it's probably software you've written yourself and hypothetically you can implement whatever logic you want. But what we have to consider is at least whether it makes operational sense. Because in an enterprise, you've got to go through probably a normal release cycle for code, which means a slower reaction time to attackers. And if you're using a simple example, I guess, if you want to block a single IP address, writing logic for that static block into your normal source code is going to be slow and messy compared to just doing it at the WAF like most people do. That's kind of the reason we have all these earlier components, is to respond more quickly and be performant and take load off of origin. So the same goes not just for blocking IP addresses, but also subnets, request header orders, and doing high-level rate limiting. Because if your app is under siege, then you want to do things quickly. With a lot of traffic, you might consider computing load and cloud bill as a result. But generally, you just want to block things earlier when you can. For logic that should live in origin, I would say that should be anything that can't feasibly be earlier in this chain, like logging of precise user behavior within the app, rate limits that are based on unique tokens and things that the WAF can't see. So things that aren't headers or just, I guess, a little more advanced in logic. If we go one step back from origin and look at in-client fingerprinting and in-client bot detection, what I mean by that is client-side code that's executing and generating telemetry data, which you're going to evaluate server-side with some closed box model and then react accordingly. CAPTCHAs are increasingly an example of this because most current ones operate invisibly or near invisibly. They don't really hinge anymore on clicking picture to fire hydrants, but rather what they can glean about your environment by just looking around. And if we move back further, looking at the WAF, your web application firewall, together with a CDN edge, that might be something like based on Varnish. You can do a whole lot with just those two things. Most of the reactive maneuvers we'll discuss, to be honest. If you're like I used to be, you might hate WAFs. Your experience might be tainted by watching them just do dumb pattern matching while you pen test. But if your WAF of choice takes dynamic updates, it can be really valuable and versatile tool in reacting quickly to assorted web attacks, not just things like an incoming script tag in a query param. It can really help you do stopgap measures before hopefully your security posture matures later. And in my demo, we have mod security as our WAF. And I guess worth pointing out now is that when a WAF blocks on its own, this is usually obvious. And it's where edge logic can help make things more effective. A lot of just out of the box WAF configurations will send back an empty body response with some headers you never see from the actual app. Maybe they use a response code like a 406 that you never use anywhere else. And overall, it's just really obvious that the attacker is going to know they're blocked when they get one of these strange responses from the WAF itself. So what you can do if you have whether you have a CDN and edge computing available or you're just running on a single box, you can use something like Varnish or a similar, very configurable caching service to disguise blocks from your WAF or really from wherever. You can execute logic that's looking at every 406 response or some other unique things that only come back from your web application firewall, and then dynamically change to some other 400 series status code. You can really dive into Varnish control language and look at the path that something was coming from. You can set the body of the response to make it look like an actual negative response from your login or payment service or whatever. And then lastly, before the next slide, if you don't have any of the things shown here, please just start with log ping. Ideally, high-level details of every HTTP request, including IP address, target path, all the headers except maybe authorization tokens or something sensitive, and then your response's status code as well. And after you have, if you have logging and nothing else, my advice would be progressing to log aggregation, something like elk stack, so you can start gleaning value from those. When you've got both things and you can really get a high level picture of what's happening within your app, you'll probably understand whether there are already bots present that maybe you weren't aware of before, or that I guess you've built an app that nobody wants to attack. For bot detection thus far, we've mentioned in-client fingerprinting, but arguably there are two other approaches, even though they'll kind of blend in with each other. These other approaches show up in different parts of the architecture we just showed. Generally, detection is going to work by assessing irregularities and abnormalities. Programmers, especially myself, have a tendency towards laziness. And if you're programming any sort of automation, this can be an especially effortful field to do things right. It's really hard to make software convincingly look human, and harder than you might think offhand. It's kind of an ongoing cat and mouse type of effort, because what worked one day will be thwarted the next. And there are new research papers, blog posts, and open source code coming out constantly, just moving the field forward, including botting and detection, offense and defense. So in that way, I guess it's not too much unlike the rest of application security. But if we break down all of the ongoing developments into three categories, you might have in-client fingerprinting, network-based fingerprinting, and behavioral analysis. Those are ordered subjectively from easiest to adulterate to the hardest. For in-client, maybe part of your application attack surface includes APIs that you expect users to be hitting with code they've written themselves, like if you sell premium API access or something, in which case this approach won't apply to you, because what it's really looking for are instances where your legitimate client code is approaching, but something's off, because again, we're looking for things that are irregular. So whichever parts of your application where you expect only your official browser-based client, Android or iOS app, or some similar client code that you've put out and that you want legit customers using, those are generally well-suited domains for this approach. You're going to execute some code within the expected clients and collect data points about the browser, operating system, device capabilities, really whatever else can be discerned from client side. And as you probably understand as a security professional, something's coming from the client, it's really prone to being tampered. So like mentioned before, this is the easiest category to adulterate, but you can make things less obvious by obfuscating your client-side code. You want to keep a secret what you're looking at to deter tampering. And then the output of this obfuscated code should yield obfuscated data. That's a payload that you're going to include on traffic to the back end, your request header. Of course, if someone has enough time and effort, they can completely reverse engineer this. That's going to be really effortful and frustrate somebody. So you kind of have to approach it that way. Commercial examples of in-client fingerprinting include Google reCAPTCHA, HCAPTCHA, G-Test, which is sliding puzzle piece, Fingerprint.js, and a slew of open source projects. These are some of my favorites listed on the slide. The current state of this field, again, requires zero or very minimal user interaction, because we've probably all clicked pictures of buses or bicycles for old style Google reCAPTCHA, but reCAPTCHA Enterprise docs now state that using their checkbox mode instead of being fully invisible doesn't really get you much. I've tested and implemented invisible reCAPTCHA across HBO Max, given presentations at their conference, and that all aligns with my views too. HCAPTCHA also states on its checkbox field that barely any users need to be challenged. That's its enterprise tier. They do have a very free, generous free tier. I would argue that it's, even though it's not open source, it is free and ethical. If you're in need of in-client bot detection as sort of a last resort or to buy yourself some time, I would definitely look at HCAPTCHA's free tier. In place of that, though, some very impressive open source is this Creep.js library. This is a screenshot of Creep.js's demo, which is linked here on the slide. This looks at an impressive number of things from your browser. It computes a fingerprint, and it can track changes as maybe you update your browser, visiting the demo. The browser might change, the installed fonts might change. You can go through the demo yourself and just see the minutiae of what this is looking at. As somebody defending an application, you can, if you'd like, log fingerprints for every user. You can even go so far as to log not only generated fingerprints, but just all of these data points. I can be a crazed, data-hungry analyst person, so I like to do that. And maybe you want to start a little simpler. You might focus on just a subset of the checks this can do. There are some, if you go through the demo, that specifically look for headless browsers, which is obviously a big indicator of bot activity, and just other means of tampering. Obviously, though, before moving on, this does take a lot more setup and initial decision-making than something like reCAPTCHA and HCAPTCHA, because those give you a confidence score, you can act right away, whereas this requires more manual setup to determine how you'd like to proceed. Network fingerprinting or network-based bot detection works off characteristics that can be observed from the edge of your architecture and possibly from your WAF. You might consider IP address, subnet, ASN, which is autonomous system number, and just a bucket of registered subnets. Your WAF can also see some HTTP request data, like everything above the request body. You can go as far as to do packet analysis and maybe look at finer TCP/IP or TLS characteristics. You'll have to note that network-based fingerprinting isn't really feasible if you're okay with users coming to you over a VPN, proxy, or other traffic anonymizer. Depends on your personal situation and your business logic. But if you're trying to thwart anybody using a VPN or proxy, because certainly proxy lists can go hand in hand with bot usage, just given the ease of rotating through them while sending requests. One example I've given on the slide is an example of looking up or trying to discern proxy VPN usage without having to look up an IP address in some database. That's become increasingly error prone. you can take an active approach and look, do packet analysis for ratio between maximum transmission unit and maximum segment size. And you won't be able to do anything at first, but if you were to log that across your whole user base, alongside, I guess, user agent or some other planar device identifiers, you can pick out abnormalities. But if that sounds complicated, these open source libraries sort of do the hard stuff for you. And if you have a single server application and that's your whole architecture, then this is actually a circumstance where looking at network data is pretty easy for you. Because in a bigger contemporary architecture, you'll have to do this way before origin. Again, as request data is bouncing around between internal places before reaching origin, you don't have an accurate picture there anymore of finer network characteristics because the data is tainted. A commercial example of this networking fingerprinting is Cloudflare's bot management, which seems to just mostly be network fingerprints. But this open source list is a combination of actual analyzers, like this Zardax tool is really good. Its author, Nikolai Sacher, I respect a lot, and you should check out his blog for anti-bot content in general. The Zardax library succeeds an older library called P0F to do passive TCP/IP fingerprinting. Then Salesforce has this JA3 library, which focuses on TLS fingerprints. And like with client-derived data earlier, you can log and watch all these things across your user base to figure out what's normal and then react from there. These other resources really just take an IP address as input and compare it versus some known list of offenders, like whether it's a suspected proxy or VPN or bot activity has been seen by prominent honeypots. I'll break those out with more examples on a further slide. Again, just looking up IP addresses can be error prone. We've seen it become increasingly error prone. I think there's press coverage of the last 6 months where Netflix and other entities that rely on MaxMind have just had increases in false positives. So your mileage may vary with that approach. What can be more reliable, sort of a middle ground, is that if you don't expect data center, VPN, or proxy traffic, you can block whole ASNs that are registered to cloud and hosting providers. You can either find a public list or do lookups yourself because the names are pretty obvious for things like DigitalOcean. If you don't outright block those users, you can just treat them differently and maybe enforce different levels of friction or rate limits, et cetera. For behavioral analysis, this is the approach that's the least prone to false positives and negatives, but tends to require a bunch of training for manual setup. You're going to consider log behavior and events and maintain, again, some idea of what looks normal and act on what's abnormal. There are some vendors that try to help with this. I don't have experience with them, but one unique one maybe worth pointing out is typing DNA. That considers only a snapshot of user activity as they're typing in their credentials. Supposedly that can be used to fingerprint with some reliability, but I have my doubts. There is another vendor, CallSign, that does not only that, but considers a wider scope of data. But we could sort of discern that when dealing with behavioral analysis, you're dealing with a whole lot of user data. It requires a lot of trust to share with the vendor. Ideally, you could evolve to have your own program which computes risk scores on a per user basis over time. That kind of makes for a better case of doing this yourself. Again, sharing tons of customer data and everything users are doing across your app requires a lot of vendor trust. For examples of open source works to help on this page, this is a mix of research papers that look at generally fraud detection tactics, keeping in mind that bots are usually trying to perform fraud, and we'll get into that with our threat profile, and then libraries that help facilitate machine learning. So again, call back to before, this is the hardest approach to adulterate, but also probably the hardest to get going with, and it's something that you kind of have to do yourself. When we threat profile and consider what bots are trying to accomplish on the internet, we'll see that they're by and large fraudsters. With login attacks really big and figuring out what valid accounts to access and take over and maybe resell. By and large, login attacks equal credential stuffing and trying creds from previous breaches, given that users are very prone to reusing creds. In the past, I understand that brute force login attacks were more common, but they seem pretty rare to me now. They're very loud with relatively little payoff. And under login attacks, you might also consider mass registration attempts. Think of that as a precursor to credential stuffing, like trying to enumerate valid users before attempting login. If you run something like a game, maybe there is some direct benefit to having a whole lot of user accounts, but usually that's not the case. For payment attacks, this includes validating stolen credit card data and/or setting up accounts to resell. Also brute forcing gift card strings or promo codes. And even if you have an obscure site, threat actor might find value in using your app to validate stolen credit card data. That can get you in trouble with your payment processor. So it's worth considering your payment flow just as fraud prone as your login. Next, what I've lumped as destructive or for ransom attacks, which would include automated injection, forced browsing, denial of service, and be coupled with port scanning. Content scraping includes piracy most prominently, but you might have worthwhile data in your app, like embedded tables of some sort. Maybe you sell programmatic access to that and threat agents are trying to sidestep it or rip it off. Altogether, considering these things, the most probable reason you're being attacked is just economics and trying to unethically eke out a living. The second most probable reason is that you piss someone off, and someone might be a team or a nation state or other non-singular person entity. Now they're coming after you, even if it doesn't make economic sense. That's a far second place because, of course, there's a cost to attack. Not just money, but also time and effort. You won't commonly come across someone that just wants to watch the world burn. And beyond a threat's motivation, we'll enumerate what the biggest, baddest attacker looks like. All of these characteristics really boil down to having lots of time and/or money, because that enables these other things. The advanced threat might have significant network or device resources. An unsophisticated attacker might come at you from a single IP at their house if they forget to turn on VPN. But as you look down a more mature scope, you might see lots of IP addresses that are sending traffic from a single data center and then maybe multiple data centers. Becoming more sophisticated yet, you'll see attacks through proxy lists. And those can vary in quality, but if you see like 47,000 unique IP addresses across hundreds of ASNs, that's not really a casual attacker. That's usually, I guess, a sign of trying to outrun IP address-based rate limits. Maybe blocks on a traffic type if you see a lot of this proxy's IPs coming from residential network space. As touched on before, you can actively detect a mismatch between the device running your client and traffic received on the back end. So a more cunning yet attacker has lots of actual devices that are running legit or very close to legit software. Headless browsers have tells, so ideally they'd be avoided. Each malicious device might be hooked up to a legitimate data connection, and together we might think of this as a device farm, which would be very expensive but not impossible. And you might also see malware that's spread across many devices that are running bot code coming at you. If you look in the right places, setups like this are available for rent. So it's not too unrealistic, but again, it is expensive. The advanced threat also has lots of attack fodder, which is just whichever input is needed for attack. Like for example, credential stuffing relies on a steady stream of fresh credentials, ideally ones that haven't made their way into Have I Been Pwned or other leaked password checkers. Also, ideally, ones that other attackers haven't been spraying yet. And if an attacker's target has CAPTCHA set up, you might sometimes see manual laborers traversing the application flow, or just sometimes you'll get an error code, or if you're doing fingerprinting yourself in-house, to see a mismatch in data, which might suggest a manual laborer somewhere is solving the CAPTCHA, and then their token is transmitted to the attacker to use on their automation. That's just a known CAPTCHA bypass is manual labor. The advanced threat also knows your application intimately and has taken the time to learn it. Beyond or in addition to that, they might just be really familiar with apps like yours. Like if you'd taken the time to learn Netflix, then a lot of that knowledge would apply to Hulu pretty directly, like DRM and content protection stuff, and what times of the day see peak traffic to disguise attack activities with. Finally, the most advanced threat probably has a decent grasp on computer science and programming themselves. You see a lot of unsophisticated attackers use a tool called OpenBullet, where you buy a config file somewhere, give it some credentials and a proxy list, and that'll just spray credits for you. You don't really need to know anything about the app that you're targeting. But the logic there can't really get that sophisticated. And when you're sharing a config like that with a whole lot of people, you can be fingerprinted on things, like as mentioned earlier, request header order that would be stable across all of these configs and be blocked that way. Getting into what I've called tactical maneuvers, but these are really just product and vendor agnostic actions to counter bot attacks. And we'll discuss from simple to advanced. For less mature teams, do more of the early stuff and vice versa. Going from top left to right, start with ad hoc blocks. And that's the simplest example, again, is when you see a single IP address sending tons of traffic and you block it. There might be a collection of IP addresses sending tons of requests, and you find that they're grouped by subnet or by ASN, so you can block those things. One maneuver I've had to rely maybe way too much on in less mature phases of my security programs has been blocking on request header order. That's literally the order in which request headers appear. And one caveat there is you probably only have an accurate picture of that right at the edge of your environment. So what you might do is run something like Varnish or set up another edge worker there to take incoming traffic and set your own header as the traffic passes internally. You might use like X-HO and have a string of colon-delimited header names in there. As you pass that down through stream, it's visible to something like your WAF, and then you can just use a normal WAF rule to block a certain request header order. So it doesn't really involve writing regex to block header orders a certain way. You set your own header and then just block out the header value downstream. Again, that probably sounds like a stupid fingerprint, and I never would have thought it to be that effective, but there's an old AOL Time Warner patent for it. And it's a valuable tool when you've got nothing else to block on. In a similar vein, you might look for other fingerprints of an attacker that seem pretty stable. Like request header order, again, is low tech, relatively easy to change around. But it's also something that you can start looking at without much effort today if you haven't ever done so before. Again, you can do it in a Varnish config. If you're running those Zardaxt or JOP3 libraries from earlier as well, you can follow a similar pattern of computing fingerprint at the edge, passing that downstream, and acting on it with your WAF if you need to. This also sort of relies on being able to look at these fingerprints in mass, which is a highlight to the importance of logging and log aggregation. So all these things sort of work together. Another ad hoc block pattern to call out is looking at username, or more specifically, email address for registration, because maybe you have a list of known temporary email provider domains and block registration anytime a match is observed. Those could be things like mailinator.com or gorillamail.com. But when you're using a list, and especially one with regular updates, that starts to get into adaptive blocks, which, again, you have a list or some data, maybe from a vendor. It suggests what traffic is good or bad. And like, I know there are dedicated vendors that track temp email domains. You could go find free lists that aren't that big, but certain vendors will claim that they have tens of thousands. So there's a trade-off in vendor alliance versus what you can find open source. Often adaptive blocks are looking at IP addresses, like maybe to do geo lookup or label traffic type like VPN or proxy. We kind of touched on that earlier. What differentiates adaptive blocks from ad hoc is that you're pulling in updates regularly yourself. So you're not manually adding things like request header orders. And the idea is to become more proactive. Similarly, I guess in a level of proactivity or rate limits, which aren't totally effective if you look at IP address alone. You might consider some other unique identifiers, but it becomes harder to do that with a WAF or in places that are earlier than origin. IP address-based rate limiting still does have some value and it can catch a fair amount of traffic. Those are things like if I see 10 failed login attempts within any 1 minute span, I'm going to block that IP for an hour, or you can play with all of those values, certainly. You will still run into some attackers that send traffic low and slow. They have a huge list, but they have a lot of time to wait to run that traffic through you. So we'll just stable the rate limits. Using other unique identifiers, again, can be more effective, but it requires some more custom logic downstream and often in origin, where you understand things like maybe values within your authorization token, or can look at things like payment credentials or username, considering them uniquely and maybe tying attempts together across a lot of fraudsters. In-client bot detection, we've gone over, but bot traps, some people might consider these part of in-client bot detection, but I would consider it any logic that only anti-automation should fail to exercise correctly. Like if we think about our happy path through the app, a normal user coming to us, they'll exercise an invisible CAPTCHA payload. That's not a big deal. That data will be included on a request header to the back end, but we know it's suspect when that's missing, and we can block just on the absence of that header. But a normal user going through our client won't ever encounter that. So that's one super simple example of a bot trap, whereas others might include hidden forms or pathways that only bots spidering your app should hit on, or host names that you've set up and somehow broadcast to attract attackers. There was a time when testing a host name for one of my apps that I left open to the world. And if you were to hit the login path through that host name instead of the official one, you never encountered basic WAF rate limiting. So some open bullet config files started circulating shady bot forums where such things happen. And when we realized this host name was still online and what it was, instead of taking it down right away, we actually swapped the logic to point. So successful logins would trigger post-compromise cleanup actions on those user accounts. So that was sort of unintentional, but I think you could achieve the same thing proactively yourself. And then a final example is client puzzle protocol. And that's sort of a proof of work that would happen in the background of your client as a means of revealing any sessions run by unofficial scripts. That's going to require obfuscated client-side code, again, like fingerprinting did earlier, but at least it'll weed out people who haven't deobfuscated that code, which can be effortful. That's also a little beyond what OpenBullet is capable of easily replicating, so it helps curb some of the distribution of automatons versus your app. And then instead of talking about how to find a block, if we were discussing how to block in itself, you might already be using edge logic to send other fingerprints downstream and block on them, log them, or take some other action. But another thing that you're well suited to do there at the edge is take any obvious responses from security appliances and make them look like real negative responses from your app. And as sort of alluded to earlier, you could use, for example, varnish control language, and if the response is a 406, and that's something your WAF sends back and only that, then you could change all of those to 403 status codes and set a bunch of response headers that look legit from your app. You could also add additional logic based on path or host name if you have multiple, and fill in the request body. I call that spoof blocking. And another thing you can do if your WAF or edge supports it is called tar pitting. And that involves keeping the connection open indefinitely to tie up incoming malicious bots instead of just sending them a response of any type. A middle ground between spoof blocks and tar pit would be just delaying response and slowing down your attackers. And if you're really sadistic, you can write some logic at the edge, which just randomly does any one of those things, or sends back some random response status code and body, and have fun with your attackers. But we should touch on that you don't need to block when you realize that something's awry with a certain user session. There are lots of countermeasures you can take against bots and suspect users or high-risk users that are more subtle. And these include your challenges, your locks, enhanced logging, flags, limits, waiting rooms, and other delays, blocking some things but not others, sending email or push notifications with reset or post-compromise link. That latter point only works if the attacker doesn't control a user's email or phone, which obviously is less common, but sometimes happens. But by and far, the best maneuver beyond outright blocking is just actual product security. There's no magic pill to get away from real product security features, because you can scan for login attackers' request headers and block different ones all day long. But if you're using WebAuthn or requiring a FIDO key or a different second factor on every login, or you switch to magic link authentication, which kind of is passwordless altogether as well, any of those setups could stop login attackers completely, and just make the need for request header order blocks on that pathway obsolete. So not every security program can get away with any of those things, but they're all pretty open technologies that you could adopt. And along the same lines, there are certain vendors that can slap multi-factor auth or password checking onto your product for you. But I argue it would be better to engineer those natively yourself and reduce vendor reliance, provide a more cohesive user experience, hold on to more data yourself, and just try to best understand what's going on in your own app. OWASP has a credential stuffing cheat sheet. There are subsections on multi-factor authentication and defense in depth that get into this. And you can also, I guess I implore you to just really learn your own fraud-prone application flows, traverse those yourself while proxying the traffic, really understand also what's happening on the back end for those requests and what different components are being hit, which might dictate where you could respond. Again, sometimes getting creative with protections, and just generally put on your security hat. Quickly touching on overall patterns for implementing protections. These refer to where you enact most of your countermeasures, and it doesn't really apply to a single server setup, but definitely does for enterprise teams with big, complex apps. These first two patterns are for less mature programs. I think you should strive for the last. I've seen situations, I would call this pattern one heavy lifter near origin. there are situations where a SecOps team really only controls the WAF. That's their one thing that they're trusted with. It sits relatively close to origin, and you're able to still do a lot with just that, especially as mentioned before, if you can set certain data points at the edge and then act on them at the WAF. This is also a place where you tend to have pretty good visibility overall. Time and again, I see that WAF logs are usually present and or more comprehensive than anything from the CDN or edge, just because that stuff is a lot higher volume. You have a better understanding at the WAF of what's going on, but it isn't as performant as this next pattern, and it yields a higher cloud bill. Edge it and forget it. This is where you're just doing as much as possible right at the edge, and you don't really care if there's decreased visibility because it's pretty cheap to do this. It's pretty performant. Again, if you haven't figured it out with my recurring theme, you can accomplish a lot with varnish control language. That's just open source catching tech, but you can get creative with it as a security team. That might mean like overloading error handling VCL to block at the edge if it wasn't intended to do so. But again, you can also spoof blocks from farther within your environment. This is fast, it's performant, it's relatively cheap, but it comes at a cost of visibility more often than not.
Sorry to interrupt, Randy. We have 2 minutes.
Oh, okay. I'll jump to my demo. My demo, I won't go into the live portion, but the code and slide and resources are all available at this link, my InfoSec blog. This puts together a lot of the open source components that we've touched on, from Varnish to Apache, mod security. There's a demo Flask web app, everything's being logged, but Varnish is used to morph any blocks from mod security, just generally anything that has a 406 response code to look like a normal negative response. So again, that's all available. That link goes to slides, it goes to GitHub, and it has all the resources that have been linked from earlier in the deck. So quick wrap up. You can be vendor agnostic. You can be really effective in countering bots if you just embrace normal traditional product security. This is an ever evolving field, but if you position yourself with more protections than your competitors, you'll probably be left alone, not have to spend all your time reading anti-bot research. Again, there's some links. Feel free to reach out to my OWASP email. I'm happy to chat about any of this further or answer any questions. Also check out Bullish Careers because we're hiring if you'd like to work together. And thanks for attending my talk.